Paige Hattie, the director of Mobius Connect. Thank you all so much for joining us for this WOW 11 session. We are super excited to have you here today. So welcome to Demystifying Digital Signal Processing for a Successful CBM Analyst. Again, we're very excited that you're here with us today for this great presentation by Praveen Gupta, one of our Mobius Connect ambassadors. So Praveen, I'm going to go ahead and pull you up here. And can you hear me okay, Praveen?
Yes, I can hear you.
Excellent. I can hear you too. Awesome. Welcome, Praveen. So I'm going to go ahead here and pass the presentation on over to you. And if anybody in our audience today has any questions for Praveen throughout his presentation, please go ahead and enter them in the question panel on your screens. And we'll have some time at the end of today's presentation for him to go ahead and answer those. So Praveen, that being said, I'm going to go ahead and we'll switch things over to you here. Screen looks good to go, Praveen, so you're all ready to get started.
Okay, so can I start?
You are all good to go.
Okay, great. Thanks, Paige, for coordinating the session, and welcome all. Good morning, good evening, good afternoon from wherever you are, from which part of the world. Today we will, touch upon this a brief but interesting topic: digital signal processing. For the CBM analysts who are there in the field doing the data acquisition, analysis, and recommendations for various machine anomalies. So, a brief about me. I'm Praveen. I'm based in Muscat, Oman, and I lead a small team of reliability and CBM practitioners at Special Oilfield Services Oman. I have electronics with MBA degree with all the relevant certifications for vibration analysis, asset reliability practitioner, CMRP, ultrasound level 1, and CRE trained. And I am authorized Mobius instructor for VACAT 1 to 3 and asset reliability practitioner training courses in Oman and virtual in the classroom and virtual modes. I have been a regular speaker across the various countries in the world related to reliability and condition monitoring topics. So today we will touch upon some of the signal processing basics, filtering, how it is applicable to condition monitoring and analysis, sampling, what are the considerations, what is the process, how what do's and don'ts, windows and bandwidth, dynamic range, spectral averaging and time synchronous averaging, trade-off between sensor sensitivity, frequency range, and some of the thumb rules for successful CBM analyst. So basically, the webinar, today's webinar, the motivation came to me during various training courses I was instructing and we were conducting for, especially vibration analysts, CAT 2 and CAT 3. So I have observed that many of the engineers, especially mechanical engineers and those who are working in the field with respect to data collection and database configuration and analysis. So they are good with overall machinery knowledge and vibration basics and signals. But as far as data acquisition and signal processing is concerned, they have some difficulties in understanding some of the advanced topics and some basic understanding of the electronic terms and signal processing do's and don'ts and some of the calculations. So I thought I will just give a brief overview of some of the terms and some of the processes and some of the jargon, so that the analysts, the practicing CBM analysts have a better understanding of the terms and processes, and they can apply in the field for more accurate root cause analysis and accurate data collection and so on. So I firmly believe in this saying by Albert Einstein that if you can't explain simply, you don't know it deep enough. So that is what I practice in my professional journey, and I try to make the topics and the subject and concepts as simple as possible, so that diverse background people in the class, in the conference, in the audience can understand the nuances, and the subject becomes interesting. And even in our training courses, we make it a point to make it relevant to them by discussing many of the real case studies in the plant, and discussing the difficulties which they are facing, and try to explain the formulas and the concepts in a lucid way, so that they can understand and apply in the field. So in terms of signal processing, whether it is a monitoring system or it is a signal FFT analyzer, the vibration analyzer as they call it, you have a sensor, vibration sensor, you have some signal conditioning, then analog to digital signal processing and the post processing. So this is the building blocks for the signal which is acquired by the vibration sensors in the field using analyzer or a online condition monitoring system, and how it is processed. So just to give you an idea. In terms of filters, filters are very important. So filter, basically in a layman language, filters enable you to look at the relevant data and filter out the unnecessary or irrelevant data. So whether the filter could be analog or it could be digital. So analog, as the name suggests, it is before digitizing the signal. Any analog filter which is applied, so that filter is applied before digitizing the signal, before the A to D, analog to digital converter, which is there in the analyzer, is active. And in the time domain, the filter, the digital integration, enveloping, any differentiation, any integration, that is also a type of filter, as we will see. And any signal processing, high frequency signal processing required to look at gear or bearing signals is also a filter, whether it is envelope, demodulation, and so on. That is also a high pass or a band pass filter, We will see more in detail what filters are all about, what are the different types of filters. But filter is essentially a digital or analog filtering of the required band of the signal to look at it more closely, what we are interested in, and eliminating or minimizing the noise or the unwanted data. That is filters. So some of the type of filters, low pass filter, as the name implies, anything which passes, which allows the input signal to pass up to a certain band and eliminate the frequencies which are higher than a certain frequency, cutoff, that is called a cutoff. So beyond that frequency, all the signal is attenuated or minimized, and in the pass band up to that frequency, the signal is passed. So this is ideal filter, but in the real world, it will be a slope. This will not be a vertical. The cutoff line will not be a vertical line. It will be a slanting line, depending on the roll off of the filter. Another variant of the filter would be high pass filter. So just opposite to low pass filter, in which you have you stop all the all the signal up to a certain frequency band and pass the frequencies above that cutoff. So that is high pass filter. Then third variant could be a band pass filter, in which there is a band from a lower frequency to a higher frequency, which we pass, and we stop the frequencies which are below this or above this. So this is a band pass filter. So enveloping demodulation could be an example of band pass filter. High pass filter, any signal in an analyzer before it is conditioned, that it goes through the high pass filter to eliminate the DC and up to a low frequency, so that the background noise doesn't impact the accelerometer signal. So that is a high pass filter. And we will see anti-aliasing to remove the undersampling. That is an example of a low pass filter. We'll see more in details. So another example, another phenomena, and another process which is used in the digital signal processing and in all the analysis is integration and differentiation. So in the frequency domain, anything which is integrated is nothing but a low pass filter, and anything which is differentiated is a high pass filter. Without going into the mathematical formulas and the digital electronics concepts, you can simply understand like this, that as you integrate from acceleration to velocity and velocity to displacement, you have the low frequency components amplified. So as you can see in this figure on the right, you have acceleration which has a high frequency components which are kind of filtered in the velocity domain and further filtered in the displacement domain. So as you can see here, as you accelerate, as you integrate, your low frequency components becomes predominant and high frequency components are attenuated. So this is another example from Mobius training material. You can see here the acceleration is attenuated. Acceleration response or acceleration signal is attenuated at a low frequency. At a higher frequency, it is predominant. In case of displacement, it is reverse. The low frequency component, low frequency range is very high, whereas it attenuates at 1 kilohertz and above. In case of velocity, it is mostly the medium frequency range. Say, for example, from 10 hertz to 1 kilohertz, it will be flat, almost flat frequency response, and above that, it will get slowly attenuated. So as you can see from here, the maximum flat response will be velocity. So velocity is therefore used for most of the general purpose machinery vibration severity. Most of the ISO standards, ISO 10816 and others, and even for fans, they talk about the velocity as a vibration severity parameter. So just to keep in mind, integrating reduces high frequency vibration and amplifies low frequency vibration and introduce a 90-degree phase shift. So there is a phase shift in the vector because displacement velocity and acceleration are vectors, not scalars. So there is a 90-degree phase shift between acceleration to velocity and velocity to displacement. So the more intricate details of the phase shift and the waveform and all we can study, we cover in our vibration analyst CAT 2 course. This is just to give you a flavor and an overview of the associated concepts. So in terms of another important consideration for signal processing or rather data acquisition is that once you increase the sensitivity, you reduce the frequency range. So in case of an accelerometer, the higher frequency means lower sensitivity, and lower frequency means higher sensitivity. So for example, if you have structural vibration and low RPM fans or cooling tower fans, you will go for a higher sensitivity sensors. For example, 500 millivolts per G, or even in extreme structural vibration cases, 1 volt per G. In that case, the resonant frequency and the frequency range of the sensor will come down. So that is the trade-off. So either there is a trade-off between frequency range and sensitivity. Higher the frequency range, lower the sensitivity. Higher the sensitivity, lower the frequency range. So this is very important in terms of the applications. So in general, Fmax of interest for any application is computed as 25 times the RPM of the running speed. And in case of there is a gearbox, it is 3.5 to 4 times the gear mesh frequency. We'll see that more in detail later. So dynamic range, you in the specifications of an analyzer, you will see that dynamic range is mentioned as a dB. So dB, say 94 dB, 144 dB. What is that dB? So dB is nothing but dynamic range is defined as 2 into number of bits. So A to D converter of the analyzer, if it is a 12 bit or 16 bit, so then you have to have the 2 exponent of that number of bits that will give you the dynamic range. For example, 24 bit, if there is a 24 bit A to D converter is used in that analyzer, which will provide a theoretical dynamic range of 144 dB. So this is theoretical, but actually it will be less because of the noise associated in the real world. It will be less than 144 dB. But this is the formula for dynamic range. Sampling. Sampling you have to do in terms of the any analyzer will not look at your analog data. It will be digitized in the real world to do compute FFT, fast Fourier transform. So when you can do the compute, the fast Fourier transform, you have to digitize the signal. Now, digitization of the signal means you are converting from an analog continuous waveform to digital bits, and that bits is your sampled waveform. So for sampled waveform, you have to sample the signal at minimum 2.5 2 times the Fmax. Fmax is nothing but the highest frequency component of that signal. So you have to minimum, you have to sample 2 times that Fmax. So if you don't do two times Fmax, then what happens? Then you have a phenomena called aliasing. So aliasing is nothing but, in simple layman terms, it is folding of the higher frequency to a lower frequency. So actually, for example, in this second figure at the bottom, you can see that if we sample these at the green points, you can see the original waveform is the blue one, but the sampled waveform, because of insufficient sampling, the frequency has come down, frequency has reduced. So it is a coarse low frequency waveform, the green one, which is the sampled waveform because of undersampling. So this is called the Nyquist criteria. This is very, very important. All the calculations, everything you have to do, assuming that in the digital world, it will be 2.56, not 2 times, because it is digital. So 2.56 times the Fmax will be the sampling frequency. So that you have to minimum, but you can do more the better. But we will see there is a trade-off between higher frequency and the resolution. We will see in a moment. But the point here is minimum 2.56 times the Fmax. You have to sample the signal to get a representative signal in the digitized world in the analyzer. So this is again another representation that if you don't sample at 2.56 times, it folds back, and the lower sampling, because of undersampling, the frequency appears to be a lower frequency. So what is the solution? So as I said before, you have to have a anti-aliasing low pass filter. So what it does, it simply filters out the higher frequency. So that higher frequency doesn't fold back to the low frequency range. So that is the simple concept of anti-aliasing filter. So basically, any sampling analog to digital conversion in the analyzer will happen after. Before that, you will apply the anti-aliasing filter. So anti-aliasing filter you will apply in the time domain. Then you will sample the. So that is the solution for aliasing problem, which is because of undersampling. So as I said, there is a trade-off between higher resolution, more time. Higher resolution is better for distinguishing the adjacent peaks in the waveform. But at the same time, the trade-off is you will have more time. The sampling time will increase. Higher the number of lines, and higher the samples. And because of higher the samples, the higher is the sampling time. So there is a trade-off between more data, greater resolution, but more time required to acquire the signal. So this we have to keep in mind while selecting the database configuration, in the analyzer for our various routes. So as an example, lines of resolution, you can see here, lines of resolution for a given Fmax. If you increase, what happens? The frequency resolution, the minimum frequency between two adjacent bins is improved. You have lower frequency, so you can have higher number of lines. Frequency resolution is higher in the sense you have more finer frequency lines, and the sample rate is same, and number of samples also reduces. So as you increase the number of lines, your number of samples also increases, and then your sampling time also is increased. So this is, one variant in which Fmax is fixed, and you are increasing the number of lines. It can happen that for a given frequency number of lines, you can increase the Fmax. So then it will reduce the resolution because you have more higher frequency but same number of lines. So we have to play. We have to, in the vibration analysis, we should understand clearly the line of resolution, the Fmax, the frequency resolution, number of samples, and sample time. So these parameters and these variables you must understand, and what is the interdependence on each on the other, that should be clear. So this is basics of signal processing. Now we will touch upon windowing. So windowing is nothing but making the end of one spectral bin as zero. So instead of starting at a non-zero value, we are making forcefully by applying a window to the spectral bin, the amplitude of the signals at start and end of that window as zero. So that is to avoid the spectral leakage of the signal and have a more smooth and error-free waveform. So that is the windowing which is applied. So windowing induces Hanning window is the most commonly used for routine route-based testing and analysis. So it is a good trade-off between amplitude accuracy and frequency resolution. Amplitude accuracy is very good. It is able to reproduce the signal, but there is a addition of windowing factor which reduces the resolution, because Fmax by number of lines, line spacing, that is the line spacing, but you are introducing a windowing factor, and windowing factor for Hanning window is 1.5. So instead of, for example, 2 hertz as the frequency resolution, because of the window factor, 2 hertz will become 3 hertz. So you will have more coarser frequency resolution as a result of window factor. But windowing is required to prevent the spectral leakage in the spectrum. So we will see windowing and averaging are the two processes to minimize the spectral leakages and minimize the noise in the spectrum before we output that as the FFT for any vibration signal. So there are various types of windows: flat top window, rectangular window, exponential window, and Henning window. So most commonly used is the Henning window. Exponential window is used for the force response test, any transient testing is there that is used. Rectangular means it is used for bump tests and impact hammer natural frequency test. Anything which requires impacts, which involves impacts, model analysis and bump testing, rectangular window is good. In general, Henning window is most commonly used for routine, route-based data collection and analysis. So Henning window example, as I said, in a one spectral, this is, by the way, taken from the Mobius training material, so which we employ to provide trainings. So you can see here in this time waveform, it is you can see here it is made zero. The starting and end of the waveform at the in the spectral window because of the application of Henning window, it is made zero before you do any averaging or any other calculation. So that the spectral leakage is minimized on any FFT spectrum. So averaging, next is averaging. So averaging, as I said, averaging is done on the spectrum. All the averages, averaging except for one, we will see in the next few slides. All the averaging is done on the spectrum. So a spectrum, you compute the spectrum and you take averages of that. Either that average could be linear average, could be RMS average, could be exponential averages, could be peak hold averages. So as the name implies, linear averages produce the FFT spectrum of the amplitudes. Averages, it takes linear averages of the four spectrums, for example, here 1, 2, 3, 4. And suppose the first one 1x, 2x, 1x, it will take the average, 2x, it will take the average, it will take the averages of all the peaks and reproduce the averaged four averages or six averages or eight averages spectrum. In RMS averaging, instead of the linear amplitude, it will take the RMS, root mean square amplitude of that and do the averages. Exponential averaging is a continuous running averages. So continuous running averages means the recent amplitude. Suppose this is the first waveform is the most recent one. So on this, it will predominate because of exponential decay, and the others will be decaying function. So it will give prominence to the most recent amplitude. Then peak hold averaging is just is not exactly averaging, but it is used for extracting the peaks at all the frequencies of the spectrum, and it is especially useful for run up, goes down, and bump tests averaging. So subtraction or negative averaging is an advanced technique in which you subtract. So for example, you are doing a bump test in which the bump test is normally done when the machine is switched off, and you try to impact the equipment with the force, and then you see the response, and that response you ascertain to find out the natural frequencies of the structure of the machine. But suppose you don't have the window or don't have the opportunity to switch off the equipment, then what you will do for doing bump test? In that case, what you do, you take the bump test when the machine is running, you impact with a impulse hammer or a sledgehammer the various components of the equipment, and you take the response with the machine is operating, and then without impacting, you take the response of the normal vibration behavior of the equipment, and you subtract the two, then that subtracted FFT spectrum will be the bump frequency spectrum, because you have subtracted the operational vibration spectrum from the bump spectrum when the machine is operating. So that is called negative averaging. Not all the analyzers give that option of negative averaging. You have to check your analyzer if it has that capability. Time synchronous averaging, this is the only averaging which is done in the time domain. All other averaging is done in the frequency domain. Frequency domain is spectrum. In time domain, it is done as it requires a tacho pulse, it requires a trigger to trigger the acquisition, and do the averaging with respect to every trigger of the or the pulse trigger based on the tacho. So as you can see here, the first waveform is the original signal, and you have the time pulses based on the tacho pulses. And because of the tacho triggering, here you can see when there is a rising pulse, there is a trigger, and when there is a falling, it stops. So that during that duration, it triggers. Then again, next onset of the rising edge of the trigger, it again start acquisition, and so on. So this is it filters out the non-synchronous. Basically, it filters out the non-synchronous peaks in the spectrum, which are not related to your 1x or the 1x and its multiples or harmonics. So non-rotational components it will filter out, and it will add up all the synchronous peaks and give you the time synchronous average spectrum. So it is useful in complicated gearbox stage. You can synchronize the reading to a particular shaft and essentially filter out all the vibration related to the other shafts. This allows us to focus on one gear at a time. So you have a multi-stage gearbox. You want to analyze and you want to diagnose the problems arising from which speed shaft, so that you can do using time synchronous averaging. So, but here you require the tachometer signal to trigger the acquisition and synchronize with the rotational RPM. Order tracking. So order tracking is nothing but normalizing the spectrum with respect to the speed. So that was averaging. This is a special technique for just normalizing the spectrum. You can see here in the left, this is the normal spectrum, which has a hertz as the x-axis. And on the right, you are synchronizing with respect to the orders or the running speed. So you can see here that synchronous peaks which are related to the RPM are amplified compared to the non-synchronous speeds. So non-synchronous will be slightly attenuated, structural frequencies, pipe strains, and other. And you can look at more closely at the rotational components. So this is run up and goes down when the speed is variable. When the speed is variable, you need this is a good technique, or variable frequency drive, or coast up, coast down. When you expect a resonance phenomena or some similar issues, then you can utilize the coast up, coast down, and have the order tracking. But obviously, but again, to note here that you require a tacho pulse for having the order, because you have to synchronize with respect to the 1x component and its multiples. So that without 1x, you cannot do the order tracking. So, we not only provide the training, we provide the complete solutions in terms of the equipment, the ultrasound, vibration, oil, electric condition monitoring, or all the services in Oman and Middle East as an organization. And we provide all the trainings as a Mobius partner, whether it's vibration analysis, dynamic balancing, alignment, asset reliability, ultrasound, and short implant training to improve to bridge the RCM skills gap, and improve the adoption of the reliability improvement culture, and minimize your machine downtime. So you can register for any of our upcoming courses scheduled for the rest of the year and next year. We will release our calendar shortly. And all the services as well we provide related to vibration and reliability and condition monitoring. So if any, and we have hundreds of case studies which we can cover in any of the session or customized training or in the Mobius training platform, which we can discuss, and we can help you to solve your plant problems and discuss. So to summarize, it was a very quick and interesting, topic of digital signal processing. So some of the key points, garbage in, garbage out. So if you don't collect the quality data, all your analysis and root cause analysis recommendations and maintenance corrective action will not be accurate, and you will have a false sense of security with respect to your equipment, or you will have alarming anticipated situation where actually the machine is operating normally. In neither of the cases, you are wasting your time and energy. So hence, the quality data collection is the key for accurate prognostics. Sampling and lines of resolution are very important for representative machine data. So if you, as I explained, if the machine is not, if the data is not sampled correctly, then you will have an undersampling, and you will assume some frequencies which are not actually, which can be called as ghost frequencies, which are actually not there from the machine, which are folding up of the higher frequency because of undersampling. Windows are very useful and necessary for minimizing spectral leakage. Averaging reduces the noise and smoothens the live signal. It doesn't eliminate the noise, but it reduces the noise and smoothens the signal. Higher vibration sensitivity, there is a trade-off, as I explained, higher sensor sensitivity and higher frequency response. So if you have higher frequency sensor sensitivity, you will have lower frequency response. And if you have higher frequency response, you will have lower sensor sensitivity. So there is a trade-off. Time synchronous averaging is the only averaging applied in the time domain. All other averaging are applied in the frequency domain. And this is the only averaging which is useful for noise elimination and data acquisition and analysis for complex gearbox signals. Order tracking normalizes the spectra with tacho signal trigger and useful for varying speed machines. So I will conclude my presentation here. So this is, I'll say, basics of digital signal processing. I will cover in another webinar part 2 of this sometime later, in which I will go into various other topics for data acquisition, for measurement errors, and thumb rules for accurate data collection and data acquisition, and so on. So thanks for your time, and you are encouraged to join Mobius Connect and our Oman community. Any of you are interested, you can write to us, or you can join from Mobius Connect. And thanks for your time for today. And reach out to me for any of your condition monitoring reliability problems at site, issues. We have a working team, experienced certified team available. We can help you in the diagnostics and correcting your problems.
All right.
So feel free for any questions, and I will be happy to answer those.
Perfect. Thank you, Praveen, for that great presentation. So as Praveen mentioned, guys, we're going to take a few minutes here and switch over and open up the Q&A session. So if anybody has any questions in our audience and you haven't already asked them, go ahead and enter them now in that Q&A panel and submit them for Praveen to answer. Again, just as a reminder, your questions will be answered and asked anonymously, so no need to worry about getting called out whatsoever. And if we run out of time here and don't make it to your question, we'll be sure to share those with Praveen so he can circle back with you once the webinar is completed. So Praveen, to get started here, the first question that came in during your presentation, this person is asking if you have any examples that you could share of exponential averaging.
Okay, yes, we have some examples of exponential averaging, and that is we have done some case studies, some field investigation earlier. So I can share on the email if you can write to me later.
Yeah, of course. We'd be happy to share that with you, Praveen, afterwards. So, to whoever submitted that question, we will be sure to circle back with you. And then this next question up here, Praveen, this person is asking, how effective is negative averaging if resonance is taken into account?
So resonance, if it is there, then it will be helpful. That means the machine is operating under resonance. Then with the resonance, machine is operating, and you have the structural frequencies and the rotational component together. So what you will do, you will take the spectrum when the machine is operating, and then you will, I mean, with the impact, you will take the spectrum, and then without the impact, without you will take the spectrum and the machine is operating normally, assuming it is operating under resonance. If it is not operating under resonance, that will technique and that negative averaging will not be helpful. So if it is there, then yes, you will take two spectrums, one spectrum with the impact using your impulse or sledgehammer, and another spectrum with the normal operating condition of the equipment, and then you will subtract the two and you will obtain the bump spectrum or the natural frequency spectrum, based on which you can calculate the natural frequencies of the equipment. So
All right.
sorry
Those
for
are
a long
some
explanation, but that is the thing. If you have any further questions, feel free.
Yeah, those are some great questions, guys. All right, so moving on to our next one up here, and we have a few more minutes, everybody. So if you have any questions, keep them coming. And again, if we don't get to all of them, we'll be sure to share them with you, Praveen. So this next question that we have here, this person's wondering if you wouldn't mind, Praveen, reviewing the pitfalls of undersampling again.
Okay, so undersampling, basically, you are not sampling at the what you call the required number of samples. So you are taking less samples, because of which, maybe I can share that screen again. One second. So I can request for the sharing again. One second, just hold on. Okay, so the time it takes, okay, it is got. Okay, you can see my screen.
Yep, we're not in full screen mode, but we can see the screen, yes. There
Okay,
we
so
go.
just to elaborate on this particular waveform, you can see here the original waveform is the blue one, which has, say for example, from the first bottom peak, negative peak, to the fourth negative peak. There are fourth negative peak. There are four instances of the negative peak in this yellow 1, 2, 3, 4, 5 divisions. So this has blue is the original waveform. This has a particular frequency, right? The frequency is number of negative edges in this five yellow bins. But actually, this is the actual waveform. But you have sampled the sample waveform is the green one. So you can see 1, 2, 3, 4. So this is not even completed half of the positive waveform. So that means this is the frequency is very low, because the positive to negative and negative to positive, the whole frequency of the green waveform is 10 times lower than the original waveform. So this happens because you have taken less samples. Suppose the first green sample and the second green sample, instead of that, you take two more additional samples in between. So the more the samples, the more will be the representative frequency of the sample waveform compared to the original waveform. So here in this particular case, you are not representing the original frequency correctly, because you are taking less samples in the given time interval, and hence there is an error, and you are folding. I mean, you are seeing a lower frequency in the spectrum, which is actually not there in the spectrum. Because of the sampling, you are introducing a lower frequency peak in the spectrum. So this is undersampling, and this happens because of lower sampling. If it is still not clear, you can speak to me, or you can write to me later.
All right, perfect. Thank you, Praveen, for that. All right, now our next question, and this will be our final question for today, but if anybody has any additional questions for Praveen, go ahead and enter them anyway right now in the question panel, and we'll be sure to pass those along to him. But Praveen, our final question for today, this person is asking if you could explain the physical significance of aliasing and its use in CBM.
Okay, so I think I have answered that question just now. So aliasing, what we are doing, anti-aliasing, aliasing is nothing but, as I explained in the this waveform. It is the sampled waveform is basically folding the original frequency, which is a higher frequency, to a lower frequency, and the erroneous or ghost lower frequency is appearing in your spectrum, which is not the actual machine anomaly or machine spectrum, machine frequency. It is a ghost frequency because of the undersampling. So this is aliasing. Your aliasing is nothing but folding a higher frequency, actual frequency, to a lower frequency because of undersampling. Now I have also explained you how to eliminate this by having an anti-aliasing filter. So anti-aliasing filter is nothing but a low-pass filter in which whatever is the selected fmax, when you select a particular fmax in the analyzer, it filters out the higher frequencies, all the higher frequencies from that point onwards. So that higher frequency will be filtered out, and hence there will not be any folding back of the frequency above fmax back into the main frequency spectrum. So that is the the concept of anti-aliasing filter, to eliminate or minimize the effect of aliasing onto the spectrum and have a representative signal which is accurate and which can determine the frequency components in the spectrum, which are accurately and representatively coming from the machine, not any effect of undersampling.
Perfect. All right, Praveen, thank you for that explanation. That's awesome. So like I mentioned, so that was our final question here for this session today. Praveen, was there anything else that you would like to add before we begin wrapping things up?
No, thanks. Thanks for your support, the page and the Mobius team. And I am, privileged, and I have enjoyed this session. So this was just the beginning of an overview of digital signal processing, just for the uninitiated CBM analysts who have any issues with the digital signal processing topic in general in Mobius courses. And feel free to reach out to me anytime. I will be happy to answer the queries, questions, or comments, or feedback.
Perfect. Yes, you're always super responsive. And thank you again, Praveen, for presenting, sharing your knowledge. As always, we appreciate you. What a great way to start off WOW 11, honestly. So thank you, Praveen, so much. So guys, just a few moments here before we wrap for attending WOW 11. We are super pleased to provide you with 50% off of your conference pass to the upcoming CBM and Reliability Connect live training conferences happening in Mexico coming up here in a few weeks, and also in Australia later this year. So any of you attending here today, you can use code WOW50 to reserve your seat to take advantage of this special discount. These events include certification training opportunities, hands-on workshops, case study sessions, you name it, we've got it. Any opportunity to keep you guys learning and up to date. You can visit mobiusconnectconference.com to learn more about these live and in-person sessions. You can also find the link to register in the follow-up email that you'll be receiving after this webinar. And then coming up next here, as I mentioned, we are just getting started with WOW 11. So coming up next here in about an hour, we have Going Beyond: How Limitless Asset Health Management is Revolutionizing Industry 4.0, presented by Christian Bank. So if you haven't already signed up and you would like to, go ahead and jump on back to the attendee hub and you can just click join session. You don't need to do any formal registration since you guys are already signed up for WOW 11, and you can tune in if you'd like to. If not, I hope that we'll see you another time throughout the week at another WOW 11 session. And then just as a final and quick reminder, please be on the lookout for an email from us containing the on-demand library access, which will include a copy of Praveen's session from today, and also that'll include your certificate of attendance for tuning into WOW 11. So be on the lookout for that email. And then if you guys, as always, are interested in engaging with other industry professionals, or if you'd like to participate on the industry's live feed and forum discussions, you can do so on Mobius Connect by visiting mobiusconnect.com, or you can go ahead and create your free profile and be sure to follow us on all social media networks at Mobius Connect to stay up to date with all the latest community happenings. Feel free to share your certificate of attendance for this week and tag me, tag Mobius Connect, tag our team. We always love to support you guys in your learning journeys. And of course, if you have any questions whatsoever as you navigate WOW 11 this week, or just any suggestions of topics you'd like to hear in the future, you can contact our team at info@mobiusconnect.com. Thanks again for joining us here at our inaugural WOW 11 session, and we will see you hopefully again throughout the week. But otherwise, stay safe, guys. Enjoy the rest of your day, and we will see you next time.